Friends here, so I don't need to be so formal, but I'd like to thank Boyan and Eduardo for the invitation to talk in this meeting. I'm going to talk about some problems I've been working lately, some ideas on you are all experts, so I don't need to be very detailed in the beginning as I planned, but some ideas on how to substitute, for example, Nihari Manifold for another manifold and solve some PDE problems which were not solved up to now because of the constraints that we cannot apply Nihari, for example. So that's some ideas I've been working lately. I'd like to, let's say, as usual, I start with this physics problem because that's where it always started for me. With some Italian friends, I've been working on these equations that come from a light beam that crosses media. In the beginning, we studied some systems which, which were like super quadratic, homogeneous nonlinearities. And then we started studying some problems which are called problems with saturation, because as the intensity of the light goes to infinity, this nonlinearity tends to a constant. So it's asymptotically linear in this sense, and it goes to the 1 over saturation parameter. These models appear in the physics problems, and they are very interesting by themselves. And then the equations also brought some interesting obstacles that we had to face. So that's how I started working on this kind of equation. So today I'm going to talk on a problem that has a nonlinearity which behaves like this, asymptotically linear at infinity, and how we manage to face some problems with this kind of linearities. Okay, you see here as S goes to 0 in this problem, then you end up with the cubic Schrödinger equation, and that's an interesting thing on these problems. Of course, if you don't have saturation, if the saturation goes to 0, you have a model that doesn't have saturation in it. So another thing that we see is that if the saturation depends on the point of the mass of the media, so you have a non-autonomous nonlinearity, and then it also brings some obstacles to the problem. Okay, so the general problem that I'm working is this to solve using variational methods. As you all well know better than me, we associate a functional, and then we have to find critical points for this functional. In order to apply, for example, mountain pass theory and other theories, you have to pay attention to two different things on these problems: the geometry of the functional and the compactness of the problem. We are going to face difficulties, for example, in the compactness as usual, because since we are not in a bounded domain, so you start by having a problem with compactness. But let me show you how this is just a review. I thought that other people would be here that are not specialists in the variational methods. So usually what we do in the superquadratic problem, we think of nonlinearity like u to the cube, for example, and then you can get compactness in that sense of variational methods. The geometry is easy because u to the cube gives a good geometry to the functional. It goes at 0, it has a mean, and then it goes up and down, has a mountain pass geometry. The problem is the compactness. So in order to face the problem of compactness in Rn, for example, we can use radial symmetry, because the H1 radial functions are the Sobolev embedding the LPs are compact, so we recover compactness. That's how we do, and there are celebrated papers on this, like beta-stick Lyons and all the things that came from then on. So this is no problem once you assume you're working in a radial symmetric problem. For example, V is radial and F is radial in X. Okay, if you don't have the symmetry, radial symmetry, you have to recover compactness from other informations in the problem. So, for example, in this case, you have, if you have a potential here, or F is like this, and you have the A of X on this, like the saturation parameter here. Not the saturation, but some information on the media at each point. So you have the inequality for the functional with respect to the problem at infinity. I'm not going to detail here, but these are problems that V of X goes to V infinity at infinity, and A of X goes to A infinity at infinity. So you have a problem at infinity, and you have the real problem. In this sense, you are in good shape, because then you can apply concentration compactness of Lyons and recover compactness for the problem. So this is the good situation, the good... for example, if you have the information, you have this, and also if you have an information of f of s with respect to s over s increasing in s, then you project this problem, the u's, which are not zero, in what we call the Nihari Manifold. This is a manifold where the real solution's critical points are going to exist, and other functions too. Here, the I prime of u projected on u is 0, but if you have a critical point, the projection on all phi's are 0. So this is a candidate of the solution should live in this manifold. So we use this manifold, assuming that f of s over s is increasing, and then you end up getting compactness in this problem and finding a solution using minimization on n.
You're assuming that the dimension is not too high to be 3.
Yes, I put 3 here.
Less than critical.
Yeah, less than critical.
So n should be 3.
Yeah. So this should be a p here with p less than 2 star minus 1. Yeah. Just since you're all specialists, you understand what I mean. I put 3 here just to remember the very good example, but anyway, I am always thinking of a problem that is subcritical. Okay. The bad case is this one, when you have the potential or the non-autonomous nonlinearity with the opposite inequality. So in this case, you are in a bad shape because the concentration compactness of Lyons does not apply directly, and then you lose compactness for this problem, and that's usually a constraint, let's say, to solve this kind of problems. But again, if you have f of s over s increasing, you project on the Nihari manifold, and since the mountain pass level, the ground state here is not assumed because the inequality is in the reverse sense, Benchi-Cerami and also Bari-Lyons found a solution on an upper level constraining to n and another set, which is the barycenter 0, for example, in the case of Benchi-Cerami. So this is the bad case, and I'm doing this review because I'm going to need this point. So when, as you know, if you have the V infinity like this, potential V of x, this is the good case. And if you have A infinity, and for example, something like this, A of x, is a good case, because of compactness, and you have I of u less than I infinity of u. And this is the easy case. I call easy, it's not easy, but the well-known case. If you have V infinity, and then the potential is coming from above, or A infinity, and the A of x coming from below, this is the difficult case, because the you have the reverse inequality to use concentration compactness, so you have to constrain the problem to a different set, which it would be Nihari set, because all candidates for solutions live here, and something else that puts you in an upper level of energy where you can have compactness. So that's how it's done. Here, because the nonlinearity is super quadratic, it's no problem to have to satisfy this condition and to project on the Nihari manifold. So for this kind of nonlinearity, if you have f of u, for example, like u cubed, then the Nihari manifold would be homeomorphic to the sphere, and all functions project on the Nihari manifold. So this is used when you are solving the problem and you're comparing the energies. So this is the good case overall, because of the nonlinearity. Okay, if you are working in an asymptotically linear problem, then, okay, many authors study this, the existence of solution here. Berestic, Lyons, Bartolo Benti Fortunato using radial symmetry, so you don't have the problem of compactness. Jean-Jean and Tanaka and Stuart Zoe, again using radial symmetry here. Here they use the right comparison, so just a brief review on the subject. But let's just focus on the two references that are closer to what I'm going to do. The work of Jean-Jean Tanaka, 2004, and Costa Teirani, 2001. They have there the potential which is in a good direction, so they get the correct comparison with the problem at infinity. And here again the same, but they are assuming this. This is the point that I'm going to call the attention, because in our case, or in the kind of problems I have been working lately, we were trying to, let's say, not assume this condition and see how far we can go. Since when you are assuming this f of s over s increasing, in the asymptotically linear case, you don't have the projection of all functions anymore. So if you have a nonlinearity, which is, for example, something like this, just an example as I did there, the projection is not going to be for all functions, but anyway, you can get some functions to project on Nihari, and this is going to be enough. Some don't. Some functions don't project on Nihari in the sense that T of V belongs to Nihari, no. But for other functions, yes. T of U is going to belong to Nihari. And this is going to be enough in this case to solve the problems again in the same way as they did for the superquadratic nonlinearities. So again, you project on Nihari. Whoops. And the thing, let's say, behaves well. You don't need all functions to project, but then you find some functions that project, and again, but here, if you are assuming that is increasing. So what I'm going to talk about is a problem that is asymptotically linear and has its natural difficulties because it's not super quadratic, so you don't work as in the mountain pass theorem as a super quadratic nonlinearity, and we are not going to assume this kind of monotonicity of the function f of u. So the nonlinearity is going to have a small order close to 0, asymptotically linear at infinity, and then we assume some conditions that is going to give, for example, that a Cherami sequence, which replaces a PS sequence for these problems, that the Cherami sequence is bounded. You need some restrictions of this kind, but this replaces f of s over s increasing. So once you assume a hypothesis like this, it is weaker in the sense that I could have f of u over u, for example, or f of u. Here is asymptotically linear to s, to u. But then it can come up and down, and then go to the linear function at infinity. So we are going to think of this kind of nonlinearity, and then from then on, you cannot project on the Nihari anymore because you don't have the resources, let's say. You don't have the tools to do that. So what we do is, okay, another difficulty that you have on a problem that is not f of s over s increasing, and working on a set that is the bad case. So we're going to work on, not with this hypothesis and the hypothesis on the functional, which is the bad case. So in this case, we have the wrong inequality, and you have a problem of compactness again. The model problem, as usual, is this. This is not a good model problem. It's in the initial, it was our, let's say, model problem, but this is a good one because it satisfies this hypothesis. But even if you think with this model, in this model, we are not going to assume that f of s over s is increasing in our proofs. So just to have an idea. And this is just an idea that the v of x is coming from above, and it's the bad situation, the difficult situation. Okay, so what did we do? Since we cannot project on Nihari, and we don't have let's say, the hope to have these projections on the Nihari manifold, we decided to use another manifold which could be, let's say, by rescaling, have some projections and help us in this problem. So what we do is we use what is known as a general Pohozaev identity. Any solution of a problem like this satisfies a Pohozaev identity when it's autonomous, when it's not autonomous. This is the version of the... So if you have a solution of a problem like this, which is ours, it should satisfy a condition like this, where the G large is the primitive of G small in the U variable, okay? So what we do is, since the candidates of our critical points have to live in this set, we define a set J of U equal to 0, which are the functions that are going to satisfy Pohozaev identity. Not all functions that satisfy Pohozaev identity are solutions, but the solutions are going to live there. So let's look for a solution there, in this subset. So we prove that these points, which satisfy Pohozaev identity, is a closed set. It's a C1 manifold once you have some hypothesis on the V, which I'm not going to talk now, but anyway, with some hypothesis, just general hypothesis, you have that it's a C1 manifold, and all functions that live in the P Pohozaev manifold are bounded from below. So you have a lower bound on this manifold, therefore the functional is, the functions that live there are not zero and have norm. Here is wrong, have this norm, this is a mistake. Have the H1 norm bounded from below by sigma. Okay, so you have the ingredients of a good manifold where you should look for a min, and a min on this manifold, if this is a good manifold, would be a solution for our problem. That's the idea. Okay, in order to have this that I just said, that a min in this manifold is a general solution, you have to have that P is a natural constraint for the problem. Once you find a min on a constraint min, it's going to be a critical point in general. So we get this by assuming some hypothesis on V of x in general, or at least in our case, the V of x has to be decreasing to V infinity, that's all. But doesn't need to have any kind of symmetry. The autonomous version of this was proved by Chata in '85 in order to solve this problem. So our first result is this. Assuming some hypothesis on V of x, which is basically that V of x is like this. Oops. And the hypothesis on the F, which are just small order close to zero, asymptotically linear at infinity, but not anything like this, f of s over s increasing, then the infimum on the Pohozaev manifold is not going to be a critical level for the function I. So we have the same problem as in the superquadratic case for the bad case. You don't have the critical level of the infimum on Pohozaev is not assumed, so you have to go above this level in order to find a critical point for the function and the solution for your problem. So this is not assumed. And, okay, what is the idea then from now on? Since we are substituting the Nihari by another manifold. The idea is that not the Pohozaev manifold, not all functions project on Pohozaev. This is true. In order to project on Pohozaev, and the lemmas now are going to talk about these projections. In order to project on Pohozaev, what we do to project on Nihari, you multiply TV and see if this is here. This does not work in our problem because we are not in a homogeneous, for example, nonlinearity. So when you are in a homogeneous nonlinearity, you have T of V to the P, for example. Then you have TP, VP, and this comes out and it helps. But in our case, we are working in a nonlinearity, which could be, the primitive could have a log term. For example, the primitive in our case could be, in the model case, for example, would be log 1 plus u squared, for example. So this log term, once you multiply by t, the t does not come out. So this is one difficulty in this kind of nonlinearity, this asymptotically linear. You don't have homogeneity, So it's not easy to work with the multiple of the vectors v. So what we do is, in order to project on Pohozaev, you rescale. You rescale and project. But because the problem is asymptotically linear, not all functions project on Pohozaev. And this is going to be a difficulty. But even so, the ones that project are going to be enough to solve the problem. So, to deal with these projections, we consider, for example, the problem at infinity. The G infinity is the nonlinear terms except the gradient term. So if the integral of all the linear and nonlinear terms except the gradient term is positive, then we are able to project any function, okay, or this function on the Pohozaev manifold associated to the general problem and to the Pohozaev manifold associated to the problem at infinity. So this is the first step where you deal with the projections. What functions can you project? Not all, but if they live in a set like this, you are able to project. So, if you are able to project, then you can go on and take more information on this. For example, if a function lives in the Pohozaev manifold of the problem at infinity, then this is positive because the Pohozaev identity gives that this is equal to the L2 norm of the gradient, which is positive. Then, if this is positive, you can project. So you can project in the Pohozaev manifold of the problem, the real problem, not the problem at infinity. So you come from here to here, and the theta that projects, the rescaling that projects, is positive, bigger than 1. This is going to be important at the end of the reasoning for the proofs. Again, if you have a function that lives in the Pohozaev manifold of the real problem, then you are able to project on the Pohozaev manifold of the problem at infinity. And this you can do with a theta less than 1. So, if one lives in a Pohozaev, you project in the other, and vice versa. But if you don't have hypotheses like this, you don't know if it projects. For example, you could have a V that doesn't project at all. This does not happen in the superquadratic problem, but happens here, and but it's not going to harm the ideas, let's say. We have enough if we have these two projections. So, what we do is, you take a function, for example, in the Pohozaev manifold at infinity, you translate, it's going to be again in the Pohozaev at infinity because of translation invariance of the problem at infinity, because the problem at infinity is autonomous. Then, since you know that this thing is here, because of the other lemma, you project in P, in the Pohozaev manifold of the real problem. In doing this, you can estimate the kind of rescaling that you are doing. At the limit, the rescaling is 1, obvious, because this is going to infinity, and the function looks up, and what it sees is the problem at infinity. So, this is natural that this rescaling should be 1 when you are far, far away. And you have a supremum bigger than 1 for all theta that do of the rescalings. This is going to be needed too. Okay, this is a technical lemma. If you are in a Pohozaev manifold, you have a lower bound for the L2 norm of the gradient of U. So this does not annulates, let's say, does not become trivial. Okay, and using all this information, we are able to prove that the min-max level, the mountain pass level C infinity, is equal to the infimum in the Pohozaev manifold. So this is because you have a problem at infinity, and you can go far, far away and look up and see the problem almost as at infinity. This happens too because we are in a bad inequality, let's say, in a bad situation. Okay. This is just an argument to prove that, in fact, you have, using that the v of x decays from above, let's say it's bigger than v infinity, you have this kind of inequalities, and you can compare p with c infinity and get the equality. But anyway, it's just to show how we use the projections. You take, suppose by contradiction that it doesn't, there is a critical point with level p. Since it's at level p, you can project on p infinity and play with these projections. That's the idea. Okay. So, in what we did is, let's say, if you review everything, you see that you cannot achieve the min in the Pohozaev manifold. So you cannot achieve the min at the Pohozaev manifold, and the min at the Pohozaev manifold is at the level of the mountain pass. It's at the mountain pass level of the problem. So this would be a ground state for the problem, because all solutions, possible solutions for this problem, live in the Pohozaev manifold. If you cannot achieve a ground state for this problem. So what we do is, you have to look for solutions in a level above this C infinity or P level. That's what we are going to do. But if you restrict the problem just to the Pohozaev manifold, you know that you are not going to achieve. So you have to do other restrictions to go up in the energy. Because if you constrain the problem to a smaller set, you're going up in the infimum. That's the idea. So we're going to use the Pohozaev manifold together. So the Pohozaev manifold, as I reviewed before, when Bench and Cherami, for example, solved this problem, the bad problem, for U cubed, for example, they constrained the problem to Nihari manifold and barycenter 0. So what we're going to do is, we're going to constrain our problem to Pohozaev manifold, because we cannot project on Nihari, but we saw by the lemmas that we can project on Pohozaev. Pohozaev manifold intersection barycenter 0. That's the idea, how to go up in the energy levels and find a solution. So we do this. The first is prove that all the levels are the same, the mountain pass level at infinity, the real mountain pass level of the functional we are working with, and the infimum on P. They are all equal. So you know that this is not going to be achieved, you have to go up. What we do to go up is we're going to constrain the problem to barycenter 0, so we define a barycenter function. This is all technical, but the barycenter function is just the physical barycenter. So if you have a function which is the barycenter of the mass. If you have a radial function, for example, the barycenter is the equilibrium point where you can hold that hat, for example. So it would be 0. A radial function centered at 0 would be 0, the barycenter. If the function is translated, the barycenter is where you put a needle and you have equilibrium. If you have two buns, in the center is going to be the equilibrium. So the barycenter is locating the real mass equilibrium of this mass distributed around by these functions, okay? So this is described here. This is the same description as used by Cherami and other authors when working on this constraint. So we need some properties. The barycenter is a point in Rn. It locates the equilibrium of the mass around it, more or less. So it has some properties. For example, it's a continuous function. Here is E, the space where you were working, minus 0. Therefore, if you have functions which are very similar in the H1 norm, they would have some close barycenters. If the function is radially symmetric, the barycenter is 0 because of the mass distributed around. And if you translate a function, then you translate the barycenter. That's the idea. So what we do is we define this. This is going to be the set where to look for a solution. Since we cannot find a solution using just Pohozaev, we restrict the functions to Pohozaev plus barycenter 0 and try to find a solution in this set. Okay? So the infimum on this set is clearly bigger or equal to C infinity because C infinity is equal to P and P is the infimum on Pohozaev. So if you are constraining with another constraint, you're going above. But then you have to prove, because of the linking theorem that we're going to need, okay, we're going to apply a linking theorem, and we know that the functional satisfies PS in a range. And this range is going to be above the C infinity level, because we don't have compactness at the C infinity level. At the C infinity level, you have PS sequence that travel to infinity forever, so you don't have compactness. So we need to apply a linking theorem in the correct range, and this correct range is going to be above this level. So we need to prove this inequality. Basically, you suppose it's equal. You have the mountain pass level, therefore, by echelon variational principle, you have a Cherami sequence. We prove that the Cherami sequence is bounded or has a bounded subsequence. In general, these things need, for example, a condition that f of s over s is increasing, but here we using another condition that substituted that, we can prove this too. So usually this is a very important, let's say, this is the core of the problem in general. For example, when you are working with a superquadratic problem, you have a PS sequence, you show that it's bounded, and then by the Sobolev immersions, you prove that it has a convergent subsequence. So the same ideas apply here. You show that the sequence is bounded, and then you need some compactness in order to have the convergent subsequence. But the compactness you get by concentration compactness arguments. So since you know all the levels, that all levels are equal, you use concentration compactness and get a contradiction if B was equal or equal to C infinity. So B is above, and then we are ready to find a solution using this Pohozaev restriction with barycenter 0. Now we have the structure of compactness. We need the geometry for this problem. And the geometry for this problem is going to be the geometry of a linking theorem. So we have to decide which sets are going to play the roles in the linking theorem in order to show that they link, they have compactness, therefore by a general linking theorem you know that there is a solution at some level, okay? So we define a function that takes points to a Pohozaev function. So, for example, you take the solution, the ground state of the problem at infinity, of the autonomous problem. Take this ground state of the autonomous problem, translate and rescale. Therefore, you project on P. This is what I was talking in the beginning. Not all functions project in P, but this kind of function translated, the ground state of the problem, autonomous problem, translated projects in P. So we are in a good set where you can construct a linking structure. So take, translate, project, you have a function at P. We are on hypothesis that the projection is unique, as when when you assume that f of s over s is increasing in Nihari, the projection is unique too. So you can define, well, this function, everything is fine, this function is continuous, it works. Okay, calculate the barycenter of this function. Since this is a radial function because it's the problem at infinity, the ground state of the problem at infinity is the radial Berestik-Lyons and all these results. Translate a radial function to y, then the barycenter is going to be translated to y. So that's... If you translate to infinity, then if you take this function and go to infinity, when the function looks up, we look up, what we see is the problem at infinity. The problem at infinity has ground state or mountain pass level C infinity. So this is what this lemma is saying. When you go to infinity, you are seeing just the autonomous problem. Here is the compactness result that we need. If you are in this range, then the Cherami sequence has, or the functional satisfies the Cherami condition. So we need to be in this range in order to apply anything, or in order to have at least the compactness. So the hypothesis we had, plus some others, that the V can go up and decay to V infinity, but this cannot be too high. So I think this is just a technical thing. I don't know how to circumvent this technical information. Even when Bench and Cherami and other authors, more recently, Ambrosetti, Cherami, Ruiz in a system, when trying to project on Nihari in that case, and use Nihari plus a barycenter argument, they also need to have some constraint in how this thing is, how far this is from V infinity, in order to put it in the correct range. So we couldn't avoid this. But anyway, so we are basically ready to use this linking argument to get a solution. We know where to be in the range, and now we just need the geometry, to check the geometry of the problem. So how we check the geometry of the problem? We want to apply a linking argument. So this is the definition of two sets which link. You need a set S. This set S is going to be our restriction. Pohozaev intersection barycenter 0. This is going to be our S. This is going to come as using that P function, and the sets link if they don't intersect with the boundary, but the functions applied, let's say, mapped on K intersect S. So this is the linking structure that we need to apply a general linking theorem. Okay. The linking theorem that we are going to apply is this version, because since we are in the asymptotically linear problem, we don't have PS sequences. The Ekelund variational principle gives a Cherami sequence, and then we prove that the Cherami is bounded, and then go on. So we have a version of the linking theorem for Cherami condition. Our functional with all that we have proved satisfies the Cherami condition in the range that we are trying to focus. We need the two sets that link. We need this comparison of the I in each of these sets, at least in S and on the boundary of K, of Q. Okay, this infimum is that B, and that B is bigger than C infinity. So this is going to be important for us in order to have the minimax level above C infinity, which is the range, and below 2C infinity, which is the range where the Cherami sequence converges or Cherami condition is satisfied, okay? So this is the structure, and now we have to define the sets and check if they satisfy these conditions. Okay. The problem for us is going to be apply the linking theorem in a linking structure and get a solution. That's it. So how do we prove this? We take Q, the P function, which projects on Pohozaev, of these points. These points are those translations of the ground state of the problem, of the autonomous problem. Okay, so take the projection, the Pohozaev, so this is going to be in Pohozaev, this Q, and the set S is going to be the intersection of Pohozaev with barycenter 0. Okay? Okay. The barycenter of a function like this is y because we just translated the ground state solution, which is radial. So this is true, and therefore this is not satisfied. Therefore, the boundary of Q inter S is empty because this is 0 and this is not 0. So you have the first geometrical condition, let's say. Now, we need the second geometrical condition, which is in the inside of Q, S and Q intersect the linking structure. So what we do is take, this is going to be the set where you're going to do the minimax for the linking. Define an operator that takes the ball with radius r, rho, to Rn by the following way. Okay, if it's taken to Rn, it's because you are taking a barycenter. You are locating a point. You're locating a point of age applied to this function in Pohozaev. So this is in Q, you apply, you end up in Pohozaev, and then you calculate the barycenter of this function. T is continuous. Because of the radius that you started with, you prove that T of y is equal to y, and then by a Brouwer fixed point theorem, you have that T of y bar is equal to 0 for some y bar. But this means that the barycenter is 0 of this y bar, and therefore this is in S, okay? Because this is in Pohozaev and has barycenter 0, so it is in S. Therefore, the intersection is not empty, and you have a linking structure of the S and Q. Once you have the linking structure, you just need now to know if you are in the range where you have compactness. But then, because of all the lemmas and all the projections we can do, you know that the minimax level of the linking theorem is in the range where you have compactness. So you have the geometry, you have compactness, you apply the theorem, you get a solution. That's all.